Well, finally, we get to talk about chemical reactions. Here's the elephant's toothpaste demonstration. That's always fun to watch with that great big huge graduated cylinder overflowing and the chemiluminescence glow. We're going to talk a lot about how to balance reactions and what they look like. Recall that some indications that a chemical change has occurred when two substances are mixed are a change in color, such as when two clear solutions are mixed, they result in a yellow colored solution. And I just put a picture up there of some of the examples from the observation lab. A change in texture, in other words, a precipitate is produced, such as when a brown solution is added to a clear solution and a cloudy solution is formed, indicating a precipitate is formed. It might be a little jelly-like, or it might be, an obvious solid settling on the bottom. When you mix two substances and you see bubbles produced, such as when you have a solid and you add a clear solution to it and you see a bunch of bubbles coming off. Now, in order to be effectively studying chemical reactions, it's important to remember how to name chemical formulas. Remember those diatomic elements and keep your note card with those polyatomic ions handy. And what we will be working on is how to balance chemical reactions. We're going to show you how to visually count atoms, and we will be identifying types of reactions. Take a minute and think about what chemical reactions are happening in your life every day. Go back to that reflection you wrote. Some of you wrote wonderful essays about where you saw chemical reactions every day. And one of my best memories is being on Waikiki Beach on New Year's with my son when he was in the Navy. So, fireworks are really fun, but in order to realize what a chemical reaction is, it's one or more of the reactants is converted to one or more products. Well, that's pretty general, isn't it? Well, another general sentence we might write is reactants, arrow, products. So again, that's a chemical reaction is a process in which one or more substances is actually changed into one or more new substances. A chemical equation is the sentence we use to write and describe this chemical reaction. It uses chemical symbols, and it kind of shows us what's happening. So here are three ways of representing the reaction of H2 with O2 to form H2O. And these are all balanced up here. The picture shows two hydrogen molecules, and we write underneath it 2H2. That's the chemical symbol. The picture shows one oxygen molecule, and we write O2 to represent the picture that we're showing. The result is two water molecules, so we don't always draw the models, we write the chemical symbols. Always reactants, arrow, products. Reactants on the left, products on the right. Chemical reactions are written by using the chemical formulas. So for example, we have methane reacting with oxygen to form carbon dioxide and water. The arrow could be to form, makes, produces, whatever you want to use to describe what's going on. So notice I'm saying this in words. You may get a question on a quiz that gives you the words, and you may have to write the reaction in your notebook and then balance it in order to complete that question. So you need to remember how to name things. One of the things that's important in chemical reactions are using the symbols afterwards, such as G for gas, L for a pure liquid. In most cases, you're just going to have water. Will either be a liquid, or if it's a high enough temperature, you may see H2O as a gas, as here. When in combustion, it's pretty hot. An S is for solid, and an AQ is there's a whole video PowerPoint about what we mean when substances are dissolved in water. AQ is the symbol we use for that. So chemical reactions, they happen, but the sentence we write are called chemical equations. So let's take a look at one. 4 moles or 4 aluminum atoms, whatever, plus 3 oxygens react to produce 2 aluminum oxide. The numbers in red are called stoichiometric coefficients. I won't be saying stoichiometric over and over again. I'm going to be calling them coefficients. Keep in mind that the subscripts are a part of the chemical formula and must never be changed once you know the formula is correct. And then remember the letters Sg and L as well as Aq are the physical states of the compound. The stoichiometric coefficients are determined in a process called balancing, and that's what we're going to be working on today. So again, what do those stoichiometric coefficients mean? In this case, we would read that as possibly 2 atoms of magnesium plus 1 molecule of O2 produces whatever, 2 formula units of MgO. And just to remind you, chemists like to use formula units for ionic compounds. This sort of means molecules, sort of. We aren't working in Berkeley with lasers and mirrors, so we're going to be working with the term moles. 2 moles of magnesium plus 1 mole of O2 makes 2 moles of Mg. That's what we're going to be doing in all practical purposes in our labs. One thing to keep in mind, though, is you may not just switch atoms or moles directly to grams by saying 2 grams of Mg makes 1 gram of O2, or plus 1 gram of O2 makes 2 grams of MgO. That's not okay. That's not how it works. So the subscripts again, the subscripts mean that's part of the formula of the compound. For example, we know that O2 is a diatomic, and it's always going to be O2. So we don't change that. So Lavoisier, way back before they knew much about atoms at all, using lots of glassware and gases, came up with a law of conservation of matter by weighing these gases against each other before and after reaction. It's kind of cool. So all we're saying here is that what you start with, you're going to have the same amount of matter that you end up with. Might be in a different form, but the actual amount is the same. So we write each chemical equation and balance it to make sure that there are the same number and type of element on the reaction side as the product side, even if it's in a different chemical compound. Oh yes. Write all those chemical formulas correctly. Practice, practice, practice. Go back and do that naming assignment again. Practice some of that naming homework again. Now recall, we once said that I just described that Mg plus O2 could be 2 MgO, and described it as saying 2 atoms of Mg plus 1 molecule of O2 makes 2 formula units of MgO. 2 moles of Mg plus 1 mole of O2 makes 2 moles of MgO. Now if you do your conversions, 2 moles of Mg equals 48.6 grams of Mg. 1 mole of O2, remember that O2 makes 32 grams of O2, and 2 moles of MgO makes 80.6 grams of MgO. So if I was able to collect my product at the end, this would be a solid. If I was able to collect this at the end, some of you may have done this when you had magnesium metal and you burned it and you saw some light flashing and you saw an ashen powder at the end. If you heated it a little too hot, you would have seen that MgO produced. If you could have collected every single atom of that, it would have weighed out to 80.6 grams. But keep in mind that we started with 48.6 plus 32, which equals 80.6 grams. There's no matter lost in the process. Now, granted, if you're working in a real lab, you're going to spill some, you're going to leave some, you're not going to be able to transfer every single atom. But theoretically, I might even write this, theoretically, you're going to get the same amount back that you started with. Okay, so balancing reactions. You're going to count atoms on each side. The number of atoms or ions on the reactant side has to equal the number of atoms or ions on the product side. And I can't remind you enough for this. The same thing as the naming. Practice, practice, practice. I mean, really, practice, practice, practice. You get better at it after time. The first time you go through it might take you a minute or two to do each one, and eventually you'll be able to do them in about 30 seconds. Oh, yes. Don't let me forget to remind you, practice writing your chemical formulas correctly. If you are taking a long time to balance a reaction, double check those chemical formulas. They may not be written correctly. So first, write the correct formulas for the reactants on the left side and the correct formulas for the products on the right side. Such as in this case, we've got methane reacts with oxygen to form carbon dioxide and water. Methane is one of those names that we asked you to learn. So CH4, oxygen is that diatomic, so it's O2. Carbon dioxide, you know, is CO2, and water, of course, is H2O. Then we're going to change the numbers in front of the formulas. Right now, with nothing written, it's assumed that it's 1. We are never going to change the subscripts. We're only going to change the coefficient to make sure there's enough on either side. So take a look right here. We're going to do this on the next page, but you can see that I've got, if nothing else, 4 hydrogen atoms or moles of atoms on that side of the reactant side, but only 2 hydrogen atoms on the product side. So we've got to do something to fix this by changing the coefficients. We never change the subscripts. Never. Okay, here we go. And then we're going to balance those that appear. You can start by balancing those elements that appear in only one reactant and one product. I like to start with anything that isn't hydrogen and oxygen, and I usually do hydrogen first and after that, and then oxygen last. That's just me. So here's this one, and let's see if we can follow through this animation. So start with C or H, but not O. And if I look at my carbon, I've got 1 carbon on the left and 1 carbon on the right. So I'm done with the carbon. Now let's look at that hydrogen that I pointed out a minute ago. I've got 4 hydrogens on the left and only 2 on the right. In order to fix that, I need to multiply H2O by 2. So here we go. CH4 plus O2 reacts to produce CO2 plus 2 H2O. This is my addition. So now we got to see, are we done yet? Page 2. Balance those elements that appear in 2 or more reactants or products. You'll be able to do this on one page pretty quickly. So here we go. Here's our new one with the 2 H2O. Let's look at the oxygen. We have 2 oxygens on the left and 2 oxygens on the right. Oh, wait a minute, there's one more there. 2 plus 2. Why are there 2 there? This 2 means I've got 2 H2O molecules. So I have 4 hydrogens, but I also have 2 times 1 oxygen there. So that adds up to 4 oxygens on that side of the reaction. So multiply O2 by 2. Here we go. So we've got CH4 plus 2O2 reacts to produce CO2 plus 2H2O. Now, is this right? We got to check it to make sure we have the same number of each type of atom on both sides of the equation. So here it is again. Take a look. We've got 1 carbon on either side. We've got 4 hydrogens on the left and 4 hydrogens on the right. And we've got 4 oxygens on the left and a total of 4 oxygens on the right. So this reaction is balanced. This is an example of a combustion reaction. Let me just write this out for you. Anytime you have a hydrocarbon, a CXHX, and you react it with O2, the products are always going to be CO2 plus H2O as a combustion reaction. Okay? This is not balanced, obviously. So one of the ways to help determine a product and balance reactions is to classify. So I'm going to give you a few examples of classification of reactions. A combination reaction would be, this is how acid rain gets started. I have sulfur and that little spoon up here, and I'm in the hood, of course, and I burn it in the presence of oxygen. And I combine the sulfur plus the oxygen, and I produce SO2 gas, which goes on to react with the water in the air to produce sulfurous acid. Acid rain, yeah. So an example would be A plus B goes to C, a combination reaction. Those are kind of easy, and they're fairly easy to balance. The opposite of a combination reaction is, yeah, you got it, a decomposition reaction. And below, the picture shows that I have potassium chlorate decomposing under heat. Sure, I'm adding heat to it to decompose it, and it produces potassium chloride salt plus oxygen gas, as shown by the flamage when I put a burning splint in there, and it just catches on fire pretty quickly. So decomposition is C decomposes to AB. Some people might write that as AB decomposes to A plus B. Either way, you've got one reactant, 2 or more products. One you're going to see a lot of are double replacement reactions. You're going to see these in precipitation reactions as well as acid-base reactions. So this is one where we have A plus B plus C plus D, AB plus CD reacting to produce AD plus CB. What's that all about? Well, let me break it down. Remember, we write the cation first and the anion second. Now, B minus might be a polyatomic ion. It might be just an anion. Remember, polyatomic ions travel together and they don't break up in these double displacement reactions. So just keep the polyatomic ions together. And then we just are switching partners here. However you want to call this, we are switching partners. A plus is hooking up with D minus, and B minus is hooking up with C plus. But as always, we write the cation first. Now here the key is going to be to write the formulas, the new formulas that you're making correctly. So in this example, HCl reacts with NaOH to form, well, let's see what happens. We've got the H plus hooking up with the OH minus to form H2O. Sometimes I like to write that as HOH, liquid. Okay? Just looks writing a little differently, non-traditionally. And then we have the sodium plus reacting with the Cl minus to form a dissolved sodium chloride solution. Another example you may see is magnesium sulfate plus 2NaF. Now I'm going to just put the sulfate, that polyatomic ion, I like to write those in parentheses. So when I get to my product, I see that the sulfate ion did not change at all. Double check and make sure your formulas of the products are written correctly. That's an example. These are 2 examples of double replacement reactions. One that's kind of cool that we'll talk about a little more detail when we talk about redox reactions, reduction oxidation reactions. That's coming up in a little bit. is when I take an A and I react it with a BC, and the A kicks out the B and takes on the C. An example of this is when chlorine gas reacts with KBr dissolved in solution. I bubble that chlorine gas through a solution of potassium bromide, and the chlorine is going to kick the bromide ion out, and in the process take its electrons, but we'll talk about that soon, to produce potassium chloride dissolved in water and a bromine gas. So you're going to see a reddish gas come off on this one. Notice that both chlorine and bromine are in group 7. So there's a special name for this single replacement reaction. You don't need to know it, I'm just sharing it. It's called halogen displacement. And I showed this one in particular to remind you, when I say bromine, when I write my sentence out, you would need to recall that bromine is Br2. When I say chlorine, that means it's Cl2. But when it's in a compound, this is potassium bromide, because bromine is an ion when it's combined with potassium. The same thing with potassium chloride on the product side. It becomes an ion in the process. We'll talk a lot more about this coming up in another PowerPoint. Okay, so let's just look at these and try to classify them. I'll give you a second to pause and then come back. Think about it now. So you may have recognized the first one as a switching partners type reaction. Silver now is combined with the bromine, and the calcium is now combined with the nitrate. So yeah, that's a double replacement reaction. And the second one reactant, 2 products. Got to be a decomposition. And the third one, I have an A plus BC reacting to produce AC plus B. This is called a hydrogen displacement, or just a displacement reaction. And the last one has 2 reactants, but only 1 product. So yes, that's a combination reaction. So I'm going to show you some pictures here, but as I look at this, I realize that I typed in H2, and that was incorrect. I should have typed in O2. So correct that on your PowerPoint slides that you're looking at. And I could see this very carefully, clearly now. Look at the reactant side. I've got 1, 2, 3, 4 red oxygens. That makes sense. 2 times 2 is 4 oxygens on the reactant side. Let's go to the product side. 1, 2, 3, 4 oxygens on the product side. This would be 2 plus 2 oxygens equals 4 oxygens on the product side. I have 4 hydrogens. 1, 2, 3, 4 hydrogens on the reactant side, and 1, 2, 3, 4 hydrogens on the product side. They've all rearranged, and you know that when you leave hydrogen peroxide sitting on the counter, eventually it goes flat. The gas bubbles of oxygen are going to leave the solution, and you'll be left with just water behind. So that's just a picture of that balancing to make sure it works. Here's another picture of H2 plus F2. Again, just to remind you, H2 is hydrogen. Remember those diatomics. F2 is fluorine. But 2HF, let's see, where's the other one? There it is. There's the other guy. is hydrogen fluoride. Okay? This is an example of a balanced combination reaction, and also a reminder to know those diatomics pretty well. We have one hydrogen molecule plus one fluorine molecule producing 2HF, and we just don't write one as coefficients, even though I think we should. I keep writing to those chemists and they just ignore me. So I've got a bunch of examples coming up here. So when we do the examples coming up, remember the diatomics exist as, let me just remind you, we have H2, now follow me on your periodic table, N2, O2, F2, go down in your periodic table to see Cl2, Br2, and I2. And that's hydrogen, nitrogen, oxygen, fluorine, chlorine. Those are all gases. Bromine tends to be a liquid, and iodine is going to be a solid. Be sure to write your chemical formulas. Practice that naming assignment. Okay, so let's do this one. I'm going to balance the following equation and describe it in words. All right, so let's do this one together. I'm going to use a different color pen just because I can. So I have one gold on the reactant side and one gold on the product side, but I see that my chlorine, I have 2 and 3. I immediately know the lowest common denominator between 2 and 3 is 6. So I'm going to go ahead and put a 3 here to give me 6 chlorines on the reactant side. And in order to get 6 chlorines on the product side, I've got to take 2 times 3 to give me 6 chlorines on the product side. That changed the gold, the Au, so I have 2 golds now on the product side, and I correct that by putting a 2 in front of the Au. If I'm going to read this, I'm going to read it as, it's a combination reaction, and I'm going to read it as 2 moles of gold plus 3 moles of chlorine react to form 2 moles of gold 3 chloride. Remember, gold does not have a fixed charge. You could also read it on the atom scale, although we won't be using the atomic scale in our lab. 2 atoms of gold plus 3 molecules of chlorine react to form 2 molecules or formula units of gold 3 chloride. Okay, now we're going to do these together, and then I'm going to give you some Thinker Buddy questions to stop and do on your own. So I'm going to show you if you want to follow my way of balancing, and it's kind of like emptying the dishwasher. My sons will empty the silverware first and do the dishes last. I always do the glasses first. I don't know, it's just a habit you get into. It's all going to get done at the end. So let's take a look. I'm going to look at barium on both sides. Barium, 1 barium on the product side, 1 barium on the reactant side. And now let's take a look at my nitrate. I'm going to keep this whole nitrate. Notice the parentheses. I'm going to highlight those parentheses. And I have 2 of these nitrates, 2 NO3s, okay, 1 minus on that side. But over here, I'm going to put the parentheses in. Remember, these are imaginary parentheses, but I only have 1 nitrate on this side. And if you recognize this top one as a double replacement, A, B, C, D goes to A, D plus C, B, you'll recall that the polyatomic ions are not going to split up. So in order to get 2 nitrates here, all I need to do is put a 2 in front of that whole compound, the whole sodium nitrate. Well, now that gives me 2 sodiums as well as 2 nitrates now. I look back over at my reactant side and I see that I have 2 sodiums. So I'm good to go. So 2 sodiums here, checks out. Let's go to the product side again. We know we're okay with barium. We haven't changed the barium. I have 1 sulfide on that side and only 1 sulfide on the other side. So I don't have to change anything. We do not write ones in. Technically, ones are not written. If you're writing a letter to the American Chemical Society, leave the ones out. I wrote them in for clarification today. Okay, let's try the other one. Just going to go through this one element at a time. I've got 2 iron atoms or molecule, or 2 irons, let's say irons, on the reactant side. And right now, just 1 on the product side. So I'm going to put a 2 there. So that checks out. I have 2. Oop. Don't know what happened with that. 2 Fe's on the reactant side. And now I have 2 Fe's on the product side. And remember, I like to do oxygen last. So I'm going to do oxygen in a minute. I have 1 aluminum on the reactant side, but I have 2 aluminums on the product side. So I'm going to go over and put a 2 in front of the aluminums to get the 2 aluminums on the reactant side. So far, so good. Now I have to look at the oxygens. I have 3 oxygens on the reactant side. Unfortunately, I only have 3 oxygens on the reactant side, so that's good to go. So we're done. I'm going to go ahead and write a 1 and a 1. So this reaction is now balanced. Now this is one that I suggest that you stop and you try to balance and see how long it takes you. Okay, hopefully you stopped. And I recognize this as a decomposition reaction. I'm just going to jot that here. Decomp. Maybe make it a little easier. I've got 2 hydrogens on the reactant side, on the product side, and 2 iodines on the product side. In order to get 2 of each of these on the reactant side, I simply use a coefficient of 2 in front of HI. 2 moles of hydrogen iodide decompose to produce 1 mole of hydrogen and 1 mole of iodine. Remember those diatomics. Let's look at the bottom one. I have 2 silvers on the reactant side, but only 1 silver on the product side. So I'm going to put a 2 here. Seems fine until I go over and I look at my oxygens. I've got 2 oxygens here, but only 1 oxygen here. And the only way that I can fix that is to put a coefficient. I can never change the subscript. So that gives me my 2 oxygens now, but it also gives me 4 silvers. So my oxygens check out, but 2 times 2 is 4 silvers, so I can erase that, cross it out, and write a 4 above. Again, another decomposition reaction. And when you're doing these on a quiz, strongly suggest you do them in your notebook on paper and then put your answers in. Here's another example that I have set up for you already, and let's see how to balance that. One of the things I like to do when I'm balancing reactions with water, sometimes I'll write my water, notice it's an L, it's the only one you're going to see an L in this course. I like to write it as HOH. And even though it's a covalent compound, it can react to produce some ions with a metal that's very reactive, as sodium is. So when sodium metal gets dropped into water, you should look that one up and watch that video. you're going to see bubbles of hydrogen gas produced, as well as a new compound called sodium hydroxide. So let's balance this. I've got one sodium here on the reactant side and one sodium on the product side. And I have, let's see, one oxygen and one oxygen. And I have two hydrogens here, but I've got 1, 2, 3 hydrogens here. So I have to kind of manipulate this around. So I'm going to take this here and I'm going to write HOH and I'm going to put that there just to maybe help me. And if I just experiment and put a 2 here, that gives me 2 OHs and 2 NAs. So I can put a 2 here, and then if I put a 2 here, that now gives me 2 OHs in the H2O. Follow me? Then the H2, which doesn't exist like that, I'm just counting atoms, I've got 1 and 1, so I can keep my 1 there. Now you can balance this equation completely fine, even keeping it written as H2O. That'll work as well. I just like to write my HOH, my water, as HOH. Ask me if you have any questions on balancing these. This is a single replacement reaction, by the way. The bottom one is a double replacement again, and we're taking potassium sulfate, aqueous, oh, I forgot to write aqueous, and aqueous lead nitrate. And when we combine them, we see a precipitate forming, and we have aqueous potassium nitrate floating around. So again, this is a double replacement. You may have recognized that right up, double replacement. That just may help you balance it. So if I have, I'm going to keep my polyatomic ions in their parentheses just for balancing purposes right now. I see that I have 2 potassiums on the reactant side, so I have to have 2 potassiums on the product side. Well, that also gives me 2 nitrates. So in order to get 2 nitrates on the reactant side, I'd better write a 2. Oh, I don't have to write a 2 there. Look at that. I've got a 2 right there as a subscript. So I can leave that 2. So I have 2 nitrates on both sides of the equation. I have 2 potassiums. 2 potassiums. Now let's count the lead. I've got 1 lead, and 1 sulfate, and 1 sulfate. So this equation is balanced with a 1, a 1, a 1, and a 2. Sounds like a dance step. Here we go. So I have a blank slide here to kind of walk through a couple of reactions from start to finish, to find the one I want to do. Here's one. Okay, let's do this one first. H2SO4 plus NaOH. You may recall from your naming that this is sulfuric acid. And sodium hydroxide. And when they react, they're going to produce sodium sulfate. And in order to write that formula correctly, well, I don't need those parentheses. I just need a 2 there. Sodium sulfate and water is produced. And you may remember that I like to write my water as HOH. That's just a Kathy thing. So water is produced. One thing I want to point out is H2SO4 when it's dissolved in water, as it is here, let me just write AQ to remind you they're dissolved in water. These are all aqueous reactions. And of course, water is liquid. So when this dissolves, this breaks up into 2 hydrogen ions and 1 sulfate, 2 minus ion. So this is not H2 plus. That does not exist. Okay? So we have 2 H pluses. So let's go over here and try to balance this equation by just looking at the sodiums first. Let's look at the metal first. And I look at the product side and I see I've got 2 sodiums in my formula. I can't change the subscript. So I have to go back and write a 2 as a coefficient here. That gives me, I'm going to pencil in those parentheses, that gives me 2 sodiums, but it also gives me 2 OHs. And I'm going to pencil in the OHs here, and I'm going to write a 2 here, so I get my 2 OHs over here. They happen to be bonded to the hydrogen and make water, but they exist. I'm just doing my accounting. So I now have 2 H's and 2 OHs for my 2 H2Os, or HOHs. Okay? I have 2 NAs and 1 SO4 on the product side. On the reactant side, I have 2 NAs, 2 OHs. Okay, that sounds good. And over here, I've got 1 SO4. And look at there, I've got 2 hydrogens. They happen to be 2 hydrogen ions, but I'm just accounting for the atoms right now. So I've got 2 H's, which equals my 2 H's on my product side. So this would be a 1. My 2 H's exist. So this is balanced by a 1, a 2, a 1, and a 2. So now we're done with balancing, and I just wanted to point out that we can host you in a Collaborate session, and we can balance using our pen, and we can work with you to balance, and balance some more. You're going to be making mistakes. You erase, use another piece of paper, and do it again. So you're going to be using a lot of your notebooks. Let us know if you have any questions.